In the previous video, we will discuss chain isomerism, positional isomerism, functional isomerism, metamerism, and tautomerism. And as you know, these 5 are the types of structural isomerism. In this part, we are going to discuss stereoisomerism. Stereoisomerism means when compounds having same molecular formula but position of group is different in space, then those are known as stereoisomers. And there are lots of examples, as you know. So that phenomena, it is known as stereoisomerism. Okay, that means compounds having same molecular formula but position of atom or group is different in space, then those are known as stereoisomers. Okay, this stereoisomerism, it is of 2 types. One is geometrical isomerism and another is optical isomerism. Now let us discuss one by one. First is geometrical isomerism. As you know, there is a free rotation about carbon-carbon single bond. This is ethylene. So there is free rotation about this carbon-carbon single bond. That means if we take this as a carbon number 1 and this one as a carbon number 2, then as you know, to this carbon 3 hydrogens are attached. So in this way, these are the 3 hydrogens. To second carbon, again 3 hydrogens are attached. So suppose these are the 3 hydrogens. Now there is free rotation about this carbon-carbon single bond. That means we get various conformations. These are known as conformation. For example, this is known as staggered conformation. If carbon atom move like this, then what happens? Next position is like this. In this way. That means there is overlapping of these hydrogen atoms. Okay, so this form is known as eclipse form. So this is staggered form. This is eclipse form. That means due to rotation about carbon-carbon single bond, we get various forms like this. These are known as conformations. Okay, but whenever there is double bond or triple bond, there is no free rotation. There is no free rotation. That means that the position of atom or group is fixed in space. For example, now here these 2 methyl groups are on same side of double bond. Now since there is no rotation about carbon-carbon double bond, that means position of group is fixed. Okay, so in this way this form is nothing but known as a cis form. Whereas if methyl group are lie on opposite side of double bond, you see here, this is double bond. These 2 groups lie on opposite side. So this form is known as a trans form. So in this way, this is cis isomer and this is trans isomer, because there is no free rotation about carbon-carbon double bond. That's why position of group is fixed in space. Means if similar group lie on same side of double bond, then it is known as a cis form. Whereas if similar group lie on opposite side of double bond, then it is known as a trans form. So these are known as cis-trans isomers, or also known as the geometrical isomers. Okay, so the geometrical isomerism, it is also known as a cis-trans isomerism. Okay, so this is all about this geometrical isomerism. As you know, in ordinary light, vibration of this light occurs in all directions. Whenever this light is passing through a nickel prism, then we get a light whose vibration takes place in a single direction. And as you know, this light is known as a plane polarized light. Okay? Ordinary light vibration takes place in all directions, passing through a nickel prism. Then a light is obtained whose vibration takes place in a single direction. So that light, it is known as a plane polarized light. Now whenever this plane polarized light is passing through a sample, some samples rotates plane of plane polarized light towards right, or some substances rotates plane of plane polarized light towards left. So those substances which rotates plane of plane polarized light towards right are known as a dextrophore, whereas those substances which rotates plane of plane polarized light towards left are known as a levophore or a levo substance. For example, as you know, glucose and fructose, these are the two isomers of compound having molecular formula C12H12O6. Glucose is a dextrophore, whereas fructose is a levophore. Why this is so? As you know, that is due to symmetry of these molecules. And whenever we say symmetry, then that position of that plane or that group, it is in space. That means this DL4 is also a
stereoisomers.